In this video, we have started chapter 6, that is electromagnetic induction. The first topic of this chapter is Faraday's and Henry's experiment. So this experiment was carried out in different ways. One by one we will discuss. Now suppose experiment number 1. So in this experiment you can see that there is a coil. This coil is connected with a galvanometer and there is a bar magnet. Okay. So here few points are written like this one, 1 2 3 4 5. So I'll tell you all the points together in this with the help of this diagram. Okay, you can read these 5 points, but I am telling this the main uh, part of these points. Suppose this magnet, initially when it was at rest, this galvanometer was showing no deflection. Okay, and we know that galvanometer does not show any deflection, means there is no current in the circuit. In which circuit? In the circuit where the galvanometer is connected. So that means this circuit, okay, this whole circuit. Now what happened is, when this magnet start approaching, or when the magnet is brought near this coil, the galvanometer shows deflection. Though in this main circuit there is no battery or no power source, but still the galvanometer is showing deflection. Means what? There is current in the circuit, and that current arises when this magnet is in motion. When it was at rest, there was no current. Now what happened is, when this magnet is brought, or it is taken away from the coil, then also the galvanometer shows deflection, but in opposite direction. In the first case, suppose it was showing deflection towards right. In the second case, it will show deflection towards left. Next point. When this magnet is brought near the coil with more speed, then the galvanometer shows more deflection, indicating that the current produced in the coil is more. More the current, more will be the deflection. And in which case the current is more? When the speed of the coil is more. Next point, when this south pole, suppose now the polarity of the magnet is reversed. Now suppose we kept the magnet like this. Okay, this side is south, this side is north. And then when it is approaching, when this is approaching towards the coil, south pole, then also the galvanometer shows deflection. But when north pole was approaching towards the coil, if the galvanometer was showing deflection in right hand side, when south pole is approaching, it will show deflection in opposite direction, means towards left, but it is showing deflection. And when the south pole is taken away, then when south pole was approaching, if it is showing deflection in left, when south pole is taken away, then it will show deflection in right. So in both the cases it is showing deflection, and this deflection is somehow related to the motion of the magnet. This is the first experiment. Okay, and whatever I said just now, everything is written in these points up to point 5. You can go through. Next, conclusion from this experiment. What conclusion was drawn? Okay, the conclusion is that whenever there is a relative motion between a closed coil means this one, and a magnet, this one, induced EMF is set up across the coil, and hence induced current flows through it. Induced EMF means some voltage which is induced. Which is induced means which is not coming directly from a battery, but this is induced by what? By this magnet. Okay, and since voltage is induced, certainly there will be some current also. So that's what is written here. Current flows through the coil. Next one, large induced EMF or current is produced if the coil if the relative motion between the magnet and the coil is large. Relative motion large means, I told you that as the velocity, as it approaches fast towards the coil, the amount of deflection increases. That means what? Amount of induced current increases. Okay, and the third point, induced current lasts in the coil so long as the magnet moves with respect to the coil. As the magnet stops, then the induced current disappears. That means the galvanometer does not show any deflection in that case. So these are the three conclusions drawn from this experiment. Okay, again the same person, they carried out this kind of experiment also. Next one, experiment 2. See, this part is same with this, only in place of here there was a bar magnet, here there is a solenoid, and we know that solenoid behaves like a bar magnet when current flows through it, right? So certainly this observation and this observation will be same almost. So there is a solenoid, and this solenoid is connected with a battery, and as soon as current starts flowing through the solenoid, it becomes a magnet, and as this solenoid is in motion, this side or that side, south pole, this is north pole, south pole, or this is south pole, north pole, the same kind of result will be shown in this experiment also, because this solenoid and this bar magnets are actually same. Okay, so all these things are written here, that means what kind of result is shown. One more thing here, this is called primary coil. Primary coil because current is flowing through this coil, and this is called the secondary coil because current is produced in the coil without any battery. This current is what? This current is induced current. This current is not induced current. This is directly coming from a battery, but this current is induced by this. Okay, so this is primary, this is called secondary coil. So same kind of observation will be observed, and thus the conclusion is also same. So let us see the conclusion. Number 1, the galvanometer connected in the secondary shows deflection when coil P move towards it, obviously. Next one, when the coil P moved away from S means secondary, the galvanometer in the secondary circuit shows a deflection, but it is in opposite direction, just like the previous observations. Okay, when both primary and secondary coils are stationary, means none of these are moving, galvanometer showed no deflection. Okay, third one, third experiment carried out by the same persons. Okay, this one is the secondary, this one is the primary, but here you can see this coil and this coil, they are not in motion. None of the coils are in motion. There is a battery, there is a key, and there is a battery. So when the key is open, this key is open, this one, then there is no current in the coil, and thus we did not get any deflection in this galvanometer also. That means in the secondary also we don't get any current. But as soon as the key is closed, in the circuit there will be development of current. Initially what was the current in the circuit? 0. Then suddenly it got current. As it got current, this galvanometer shows deflection, and when this current is developed in the coil, then the galvanometer again stops showing deflection. That means galvanometer shows a momentary deflection, means as soon as the current develop in the circuit it shows deflection, but once the key is in closed state for a long period of time, then it does not show deflection. I think it is clear. That means as soon as it is closed, switch is on, it shows deflection. Now if the switch remain for a long period of time in on state, it will not show deflection anymore. Just at the moment it is on, it shows deflection, and then it stops. Again it shows deflection, this one, when the switch is closed. Closed means when the switch is off. Off means what? Open. Then it shows deflection at that moment. It shows deflection when at the moment of switching on, and at the moment when it is switched off. Okay, now from all these three experiments, what conclusion can be drawn, or what is common in these three experiments? Why current is produced in the second coil? Okay, let us see the common factor in all these three. The common factor is magnetic flux. Now what is that magnetic flux again? Okay, so magnetic flux means it is the number of field lines. Suppose this is a magnet. Okay, I'm telling you about magnetic flux, then we will discuss the result of it. Okay, here it is. What is phi? I have written, no? Phi means magnetic flux, means it is the notation of magnetic flux. So magnetic flux through a surface is defined as the total number of magnetic field lines passing through a particular surface. Suppose if we have this surface, okay, if suppose these are the magnetic field lines passing through the surface, then the total number of magnetic field lines which is passing through this, that is called the flux. Okay, now magnetic field lines means what? Suppose if it is a magnet, if this is north pole, this is south pole, if this is the surface, then what we know that from north pole many field lines will generate, it will pass through the surface and then it will form closed loop, it will come to the south pole like this. Okay, so through this surface many field lines are passing, so this is called the magnetic flux. Mathematically we will discuss later on this part. Okay, now let's discuss Faraday's law. Okay, what is common, right, in this three experiment? See here in this experiment, as the magnet approaches the field lines, see this from south pole many magnetic field lines are coming out like this, and then they will complete the circle and they will move, or they will enter through the south pole. Anyways, as this magnet is brought near the coil, the field lines linked with the coil is increasing, or can we say the flux is increasing, and as the coil moves away, then the field lines passing through the coil is decreasing, or the flux decreasing. So whenever the field line is increasing or decreasing, we are getting current in the circuit, because when this is at rest we don't get any current, means there should be some change in phi, change in flux, then only we are getting current, and this is the common thing in all the three experiment. See here also the same thing is happening. When this solenoid, either it is brought this side or it is taken away, then only flux, then only this current is obtained. Means what? Flux, either the flux linked with the coil is increasing or decreasing. Okay, in the third case also same thing is happening here. See, when this switch was closed, means no current was there in this coil or in this solenoid, no current. So no current means no field lines, this solenoid is not behaving like a magnet, no generation of field lines, so no current is observed. As soon as the switch is on, this key is closed, closed means on, right? Then what happens? Then current in the solenoid it starts flowing through it. As a result, it became a magnet, and once it became a magnet, now suppose if this is north pole, this is south pole, from this north pole field lines will originate and it will pass through the secondary coil, and this galvanometer shows deflection. Now once this key is closed, right, now see, suppose when no current was there, field lines linked with this coil was 0. Now suppose when current starts flowing through this coil, field lines linked with the coil becomes 100. So it will remain 100 for how much time? When current flows through this coil, for that period of time it will remain 100 only, there will be no change of field lines. So that is why momentary current is obtained. Current is obtained, then it stops. Why? Because there is no change in field lines. Only when the switch is on, that time only the change happens, change took place from 0 to 100, because initially nothing was there, then it got 100. So that means that time only the galvanometer shows reflection. And again when the switch is off means now the field lines is reducing from 100 to 0 again. So again in the secondary coil there is a change in field lines, and then only the galvanometer shows deflection. When the field lines linked with this coil remains 100, no change, then the galvanometer shows no deflection. I hope it is clear. Initially there was no current, So field lines linked with this coil was 0. When the switch is on, current increases, current develops in it. As a result, suppose field lines linked with this coil becomes 100. So there is a change at this moment. When the switch is on, there is a change from 0 to 100, and thus we get current in the circuit. Galvanometer momentarily shows deflection, then it stops. Then the galvanometer does not show deflection, because now there is no change in flux. Change in flux will take place again when this switch is off, means again it will become 0 from 100. Then this galvanometer shows deflection. So in all these three experiments, what is common? Common is that when there is a change in magnetic flux linked with this coil, then induced EMF or induced current is produced in this coil. That is the conclusion. Change in magnetic flux should be there. Okay, and that's what is written here. Finally, the conclusion. The conclusion is that this one. Conclusion. Induced EMF and hence induced electric current is produced in a closed circuit by the changing magnetic field through the closed circuit. Changing magnetic field or magnetic flux, whatever you say, it's representing the same thing in this case. So change in magnetic field or change in magnetic flux. In other words, electric current flows through a closed circuit due to the motion of a magnet with respect to the closed circuit. Okay, this is the conclusion drawn from all these three experiments. Or in other words, on the basis of this conclusion, Faraday Faraday's law is developed. Two laws are there in Faraday's experiment based on this experiment actually. Okay, now let us see what are those two laws. This one, Faraday's law of electromagnetic induction. On the basis of his experiment, Faraday stated the laws of electromagnetic induction. The first one, this is called Faraday's law of electromagnetic induction. Qualitative law means no mathematical formula is related to this. Whenever magnetic flux linked with a closed conductor changes, an EMF is induced in it. Okay, this induced EMF lasts as long as the change of magnetic flux continues. So that's what already I told you, right? When there is a change in flux linked with the coil, then we get an induced EMF or induced current, because wherever there is EMF, there will be current. This is the first one. Next one, second law. The magnitude of induced EMF is generally written by E, in a closed conductor or a coil is directly proportional to the rate of change. Is proportional to rate of change of magnetic flux linked with the conductor. Mathematically it is like this. E means electric flux, induced EMF. It is directly proportional to rate of change of flux. Rate of change of flux. Flux means what? Phi, and rate of change of flux means d phi dt. And then it is found that E is equal to, instead of writing proportional, it is equal to d phi dt. So mathematically we can say this one. Modulus of E, because here the direction was not specified in Faraday's law. It was later given in Lenz's law, that one we will discuss, but mathematically from Faraday's law we can say E modulus of E is equal to d phi dt. Okay, or E is, if I go directly from this statement, then I will write E is proportional to d phi dt, but later on it was established that E is equal to d phi dt. So better you write this one, E proportional to d phi dt. Okay, from Faraday's law, directly from the statement. Then this part already I told you about flux, but mathematically this magnetic flux phi, it is written as like this: B dot A. B means magnetic field intensity and A is the area through which the field lines are passing. So it is a dot product of magnetic field and area. Now if it is B dot A, we can write BA cos of theta for dot product. Now see here, suppose there is an area, this one, like this. Now if area is a vector, because here area we are considering as a vector, so if area is a vector, its direction is always perpendicular to its surface. Its surface is like this, so its direction will be this one, n cap, perpendicular to the surface. So this is the direction of area vector. And where is B, magnetic field? Suppose this is the magnetic field in this case. So this theta will be the angle between B and A. A means which one? Direction of A is n cap, this one. So this is the angle theta. Okay. So we get phi equals to BA cos of theta. And the definition of magnetic flux is this one. Okay. Then in next video we will discuss about Lenz's law.